Hi there everyone, welcome to the Network Freestyle. I'm Malcolm Daren
And I'm Daren Fullwell.
and we are the Network Freestylers. Today, Freestyle 105, been out for a little bit of a Cisco, like Darren's got a bit of a Cisco Live hangover.
Struggling after.
Busy with real life, so apologies about that, but we're back and hopefully got some good content coming up in today's episode. So Freestyle 105, we're starting like a sort of like a mini series here. Darren's written a blog on his own blog about the 5 principles of network design, and he'll talk about them in a little minute. So the first one in the series sort of aligns with Darren's blog posts. And today's episode, we're going to talk about network availability and network design. Darren's going to lead the episode, going to talk about something. We're not going to read from his blog, because if you want that, you could go and read it yourself. So we're going to
do a bit of whiteboarding. In the show notes, of course.
Yeah, so nothing like a little plug there.
Absolutely.
Yeah, so on that note, I've not much else to say at the moment. So I'll hand over to you, Darren, to give a bit of a background as to
no trouble.
what we're doing.
So it was one of the things that after I completed the CCDE, and obviously Malcolm, you did it. You've been through the process of looking at all of the things that you need to build into your designs as you put them together, and it kind of, I don't know. There's lots of schemes and lists of design principles that people come up with, and so on in the texts. And I wanted to kind of frame them myself, really, in a way that made sense to me and to hopefully to others. And I came up with the 5 that you can see on the screen there. It's a shame I couldn't find a word that began with S for number 1, but hey, availability.
Let's just wrap it up there then. Right.
No,
call it a day. That's enough.
Availability, the whole point of availability is what the network's there for, right? It's there to provide connectivity and access to services. So what we'll look at when we talk through availability is how to approach getting that in place. We'll step through the others in subsequent videos, but hopefully you can see what they are. Scalability, i.e. how you grow and shrink a network to suit. Security, where you put your security, what your security is there trying to do. Supportability, the what you need to do in order to make a network usable and functional and operational. And simplicity, it's a standard thing, right? No one wants a complex network, but what does that really mean? And try and tackle that in subsequent videos. But obviously today we're talking about availability, and that's kind of like keeping the lights on, I guess, really. So if you bear with me a second, we'll switch to
I mean, while you're doing that, like what really interests me about all of these subjects is that there's a blanket answer for all of them, right? So if you're speaking to a customer, or if you are a customer, it's really easy to say, what do you want from this design? What do you want from this network? Because, like, well, it has to be highly available.
Yeah.
But like that kind of goes without saying now, right? An outage to a business is basically not really an option, more often than not. But there's a lot of things that make availability up.
Yeah.
Right. So that's, I think, what we're going to try and talk about.
And we'll try and drill down into that a bit more, really. I mean, the whole point is, like you say, availability is a blanket term, and one of the things we'll come to in a sec is how that shows itself, and the things that you can do, and the things you have to consider, because it's not as straightforward as you expect as well. Again, it comes to something we always talk about, right? About the fact that, yeah, CVDs and those sort of validated designs are great, but sometimes one clashes with another, one clashes with real world, and how you make those work together is really important. So,
and it goes past dual links, uplinks on every switch as well. So,
of course.
Yeah, I mean, with the best will in the world, dual uplinks and dual links and all that are only going to operate if they're, you know, and provide. Oh, sorry, they're only going to provide availability at different levels, or they are going to provide availability at different levels depending on the configuration and the design of the network. So a switch with two uplinks could like provide different levels of availability based on other factors, not only on the network but also how the applications can respond to changes in the network.
Yeah, absolutely, and I suppose this is exactly the point I'm trying to work through here. Hopefully, it'll make some sense. But let's just draw some pictures and see where it takes us. Right. So obviously the main thing that we're trying to do with any network is to get these things, and that's a really great picture of a little laptop there, and maybe your mobile devices. Get those guys talking across some sort of network, and let's say in our case, bit of wireless maybe, connected to some wired switches, and a little access switch maybe, a core switch down here, over some routed links maybe into some sort of big wide network, into another router at the other end, and then out into some more switches in a data center somewhere, and that might be your data center or it might be someone else's, who knows. Eventually you're going to end up on some sort of compute infrastructure. I'm going to draw something vaguely approaching a sort of slot chassis based server. Could be anything, right? But essentially you've got there a series of devices that are in a path that are going to provide you connectivity from your end station over here to your server infrastructure over here, right? That's and obviously that availability is the access to all of those things, right? So it's the transport that makes all that stuff happen. Okay. Now that transport, we're talking we're talking switches, we're talking routers, we're talking circuits, we're talking any of the boxes that sit in the path there, right? And that they all contribute towards that availability of the service. But there's other things that do as well, right? So you've got security. So in there you may have firewalls, or you may have security inbuilt into those devices. So you need to consider that. There's the servers themselves and the infrastructure at the data center end of things. They need to be on the network, but they need other stuff. The software and the configuration of those servers needs to be built in a certain way. The application itself needs to be available. So the software that sits on the server needs to be up, needs to be visible, and needs to be connected through the server into the wider network. And then you've got ancillary stuff, so other sort of services that are dependent on the applications will be dependent on things like AD, like DNS, and perhaps some controllers or whatever that may be in the network that all play a part. So this isn't just about getting a packet from A to B, and we all know, right, from a network design point of view, we should never be just concentrating on get packets from one point to another. Ping isn't troubleshooting, right? This is the same theory. So you need to consider all of those elements, and the service availability is dependent on all of those things. So okay, so far, does that make sense?
Yeah. No, I mean, absolutely. I mean, it's more. I think that's you've covered pretty much everything there. I mean, the other thing is like just a couple of notes that reminded me as you were working through that. So security. One of the things that has sprang to mind when you talked about security when it comes to availability, the immediate thing that springs to mind for me is DDoS. DDoS attacks,
Absolutely.
distributed DDoS attacks, or something that, when you were putting a firewall in or internet edge infrastructure in even over the last 5 years. DDoS wasn't you wouldn't say, oh, I need a DDoS mitigation service. Now all of the service providers that I deal with now on their internet edge have some sort of scrubbing service, which comes as standard with internet links if you come over their infrastructure, but then you can pay for like an enhanced service to define policies specifically for your organization. Or there's on-premise, there's the traditional DDoS service, and this is maybe why in the past it's not, like over the past 5 or 6 years, it's not been as common. It's not picking on Arbor as a vendor, but you know, their kit could be quite expensive for like a small to medium enterprise. I know like Cisco have got they've got a DDoS service in the Firepower appliances now, which is a subscription service. I think it might only be the 4100 series that you can activate that. But anyway, DDoS, like, you know, for somebody to attack your internet pipe, all they need to know is your public IP, easy to get, and go on to some sort of site where they can rent a DDoS service. And the more they pay, the more bandwidth they can send. And if you don't have this type of service in, you are definitely at risk of your pipe being filled up and crippling your organization's internet pipe. So,
and of course there are other forms of DDoS, right? You can you know, BGP hijacking and all kinds of crazy stuff that people can do to you know, basically take a denial of service attack to your organization. So as soon as you've got a big red cloud in the middle of your network like that one, then yes, you know, that's a risk. So something you need to absolutely bear in mind. And this is why this isn't just as simple as you know, like you said before, just dueling everything up and whatever. However, that said, from a network point of view, within an organization, those sorts of things are important, right? So we'll just move on to the next little bit of drawing. So there's a number of techniques that classically we've used, and sometimes when we talk about availability, high availability, these are the things that we think of in terms of networking, right? So give us some ideas. I mean, we've talked about redundancy being a thing. Okay. Obviously, when you introduce redundancy in the network, you've got to worry about stuff like loop prevention. You've got to think about convergence and timings and that sort of thing. You've got SSO type capability, so that's stateful switchover. So if you've got two devices in a network, replicating state between them so that if you lose one, you can just fail to the other one, that kind of thing.
One that might not actually be as obvious as power consumption, because if you're putting like multiple power supplies, I've actually been in a pre-sales discussion with someone over the last few years, and the requirement was that they had presence in a data center, whatever kind of data center. It wasn't a colo, it was like a space. It doesn't matter what kind of space, it was a space, but they had an upper power budget. They were going from 6500s to 6880s versus Nexus or something like that. I can't remember the detail, but basically I had to get the wattage, the draw, like all these different types of power calculations. And I actually had to get Cisco virtual engineering involved to say, how do I work this power calculation out to send to the customer so they can just say it's going to draw this much.
Yeah.
And that was going to be the decider whether they went for, like, making these numbers up, a 3K power supply versus a whatever the bigger one was. And then that had a knock-on effect to how many line cards they could take in the next 6 months until they got the power upgraded. So in a one new switch, adding a hot swappable power supply may or may not, because you could have a 1100 watt power supply times 2 that might times I don't know, 50 switches in a place that might like mean that there needs to be a power upgrade, and that quite often happens.
And of course, if that's a constraint as well, if the power can't be upgraded in a particular location or can't support the redundancy that you're looking for, whatever, it's a constraint that makes a big difference, because obviously upgrading your power plant is like doing your cabling, isn't it? It costs an absolute arm and a leg, right? So you want to, again, it's all part of the compromise, all part of the trade-off, right? That you have to make here. I've got a couple of other things that I made a note of along similar lines, I suppose. The things like the mean time between failures of the kit that you choose, you need to consider. If you've got kit that is supporting a service that has a particular availability requirement, and it's got a very high mean time between failure, then it may be you may look to implement it in a different way than stuff that has a lot shorter one, right? Stability of the environment is an interesting one. How much change is going on through the environment, and how that needs to be supported. And obviously things like making sure you've got enough performance to handle redundancy and resilience in the network topology as well. If a big chunk of it fails, are you able to support the services you need to in what's left, and so on. And I've got a couple of
performance as well. It could be something like merger or acquisition type scenario, and then you say, right, well, let's just take ICE as a radius authentication, and let's as an example, just pulled it like from out there because ICE is on my mind at the moment, but not directly to do with this sort of thing. But let's say ICE is the radius authenticator for a wireless LAN or a wired LAN, and there's multiple different things that could potentially tip it over, because there's obviously thresholds on types of ISE deployments. So you've got like the standalone, which back each other up. You've got the medium deployment where you split the PAN and the MNT node onto the same appliance, and then have up to. So technically you could have more than 5 PSNs, but it's 5 PSNs and 20,000 radius authentications concurrently across those 5 PSNs. Or you go to a large deployment where you split the PAN, MNT, and PSNs out with up to 50 and 500k connections. But if let's say you had like the medium deployment and you done something, it could be like you run a proof of concept on a wired radius 802.1x, and let's say you were already hitting like I don't know 15,000 connections in the back end, and at the peak of the day. And you do this POC in like 4 or 5 big sites in different regions of the world, or even in UK, Europe, whatever. But at the end of the day, it doesn't care. If that deployment goes over 20,000 concurrent connections, it could start like putting high CPU up. It could knock a PSN over. It might knock the whole system over. But that concept applies to any system, not just ISE.
And take that a step further. If there's a further dependency on another system, you have a knock on, like ICE and Active Directory. If Active Directory sits across a WAN to get from your ICE to your AD servers, for example, then you've got a latency there that might cause you a problem with the latency of your authentication request coming into the PSN in the first place. And if there's a WAN problem or a link to the WAN from where the Icebox lives or the AD server lives, then that also can cause you a problem. And it may be that only happens in a failure scenario. So again, all of those things need to be brought into consideration. And so I suppose all of these tie back to some of the things we mentioned before about the other things that we're going to talk about in the grand scheme of things, the scalability, right, of the environment, what that looks like, and the requirement for scalability has an impact on the availability. The life cycle management of the platform. So if you think about it, things like things like maintenance windows, things like software upgrades. If you're having to roll a software upgrade out across a big old network, do you roll it out across the whole thing all in one go, or do you group elements of it that you upgrade at certain times based on the availability of the services that you're providing, right? You might decide, for example, in a building to arrange your access points in half and half type scenario, where you upgrade half of them in 1 hour, and then a couple of hours later you upgrade the other one, so that you always retain coverage while half your APs are rebooting. You see what I'm saying? It's those kinds of things are really important.
Yeah, I mean, I think like one of the other things that's quite well, fairly recent, as in the last like sort of 18 year to 18 months, was, for example, if you were to standardise on the Cat9Ks, which most companies will be, ISSU wasn't available until
absolutely.
So I've had scenarios where I've observed scenarios where a switch has been made from another platform to a Cat9K in a quite an important part of the network, where the only option was and then bugs. So let's take platform and scenarios out, right?
Yeah.
Let's like specifics and say new platform, probably going to have some bugs. Put it into production, because that's the only time you're going to find out what the bugs are. Right, so let's say you start off on software version 1, and then you need to go to 1.2 after 6 months, and then ISSU isn't out till 1.8, which is like 6, 7, 8, 9, 10 months or a year down the line. But it's got some, you jump a software version. Anyway, that has to be rebooted. It's going to cause an outage unless you get into things like splitting a stack and doing one at a time, and that whole thing plays into the consideration as well.
Absolutely, and that's exactly what we're talking about here, is how you manage that, and to some extent how you wrap a process around it. So this isn't even a technical consideration in that sense. It's how you approach doing it, how you educate your engineers to actually go about doing this type of work. I think that's really key. The other thing that's really important and not mentioned so far is visibility. And for me, this is probably, well, it's critical to understanding what the availability is, because the idea with visibility is that clearly you have monitoring of all the elements of your network. You know which devices are up, you know which interfaces are up, you know what the bandwidth looks like across them, you know how they're utilized and where the errors are and all that kind of good stuff. Clearly, really, really important. Important to know how a particular client connects and which point they connect to in the network and where a particular workload is that they're trying to talk to. All of that. But these are all network-centric elements. What you then have to be able to do, and it's really, really key here, is if you're looking at service availability, if you're looking at understanding how your application is functioning, you need to understand, right, how do I measure that? How do I measure response times for my application, and how do I get the visibility of that and understand where the flows of traffic that make up that application pass across the network? Not an easy thing to do, and to be honest, not that many people really have a proper grasp of this. But some really interesting tooling starting to see now that allows you that sort of visibility, and I think that's a really important thing to understand and understand well. Is how applications behave and what elements they need in order to function, and getting the visibility of that gives you then the opportunity to, right, okay, I can measure my availability of my service, and once you can measure it, you can see how well or badly the environment that you've built actually supports that availability. Really, really key.
Yeah.
So I guess these are some ideas anyway around the sorts of things that we can do to improve availability. And obviously we have some there are some there that are very classic network issues, the redundancy, loop prevention, convergence, SSO from this list. Others that are wider environmentals, but also, you know, really, really important. We'll drill down a little bit into some of these, and just to show how things that we traditionally considered as availability issues, how they feed back into this.
And I think one thing that we've not actually mentioned yet is like what's the purpose of availability? And when you're a techie and that close to, you're really only close to naturally only close to how things are performing, like in respect to is OSPF converging and or there's an outage, so users are on my back. But what availability basically comes down to, the other concepts are all obviously important, but availability is the money maker. Like if your network isn't available, the business can't make money. So it means staff are either coming to work and not able to execute their job, and like people have probably heard that quite a lot, but availability is the money maker. So if a manufacturing plant is down for 8 hours, and a whole shift of people are probably going to get sent home.
Yeah. If
a bank's WAN link is down, there'll probably be some sort of local application availability, but they probably will have some sort of threshold around what they can and can't do in regard to banking transactions.
Fall back to paper or whatever, right? But then there's the true up afterwards and all the extra work that brings to make that happen. Absolutely. Another example, distribution, right? In manufacturing, you've got warehousing that holds all your parts. You need those to be distributed out to the places where assembly happens or whatever. If the parts can't get sent to the right places, then the assembly can't happen, and so you've got a knock on further down the business, haven't you? So,
well, I've got a very quick story about when I was a project engineer. I got a job to install a non-Cisco switch into a non-Cisco stack. It was Nortel. Right, so
I thought you were going to say 3Com for a second, but
yeah, I just went over with Avaya. So when they got taken over by Avaya, and I had a job. It was when I worked at Avar, good like 7 or 8 years ago, probably now, and had a great relationship and still do. Before I continue the story, but like had a great relationship with the company. It was like a drinks manufacturer, is all I'll say, right?
Nice.
So I had a soft drink. It was more water. They were a water, still water, sparkling water, but they'd done other things as well. So I got assigned a job to install a new switch into an Avaya stack, but it wasn't just that. It was the fact that, you know, it had uplinks, it had things in a triangle, and there's an equivalent in Nortel Avaya to VSS. I can't remember what it was. I can't remember what it is, but there's an equivalent to VSS. So they had this in the core, but they actually had a triangle. Like it was a manufacturing site that they done some manufacturing, and then they also had the warehouse at the same location where lorries would come in and park and then get loaded up, and they would have like the scanners that operated on the wireless network. So a pallet would come down, they'd scan the thing, put it on the lorry, then it would go and get shipped out and delivered to shops, basically, in supermarkets too. So I had a change window of 30 minutes to, and in theory, it sounds like easy, right? But to put a second Avaya switch into our stack, so I had all the configs backed up and all that, and I think it took me 33 minutes to do. But I had the network manager from around 20 minutes saying, "Are you nearly done? Are you nearly done?" And at the time, I just felt under a lot of pressure.
Yeah.
But now, a good few years later, and I understand, how business works a lot more. There was about 6 or 7 lorries sitting waiting, and then a load of warehouse staff. So I had the the network manager standing over my shoulder saying, "Are you nearly ready? Are you nearly done?" And I was like, "Yeah, it's rebooting." And then I was getting flustered because Avaya stuff wasn't. I did do it, but I didn't do it every day, and I knew what I was doing, but it
Time
just
is money, right?
that thing. But if I hadn't got that network backup, right, the amount of money that they would that that was lunchtime when the lorry guys can come in, have a half an hour break, but the warehouse guys, like I don't know, 20, 30 warehouse guys, or however many warehouse guys, the network was down. Do you know what I mean?
Yeah.
So then, anyway, we got the switch in, and then the stack came up. But then what happened was the scanner server needed rebooted. So the wireless LAN was up. I was on, like, they were on with a laptop. They could get onto the network, and they're like, "Oh, has the switch caused an issue?" And I was like, "No, it's got to be like the application." Then nobody believed you at the start. Then they went and rebooted the server, and then they started scanning the stuff. So the 30-minute change window, and that kind of just like highlights 30 minutes. There's never a good time to do it in an environment like that, but 30 minutes is like a gold to them.
But like you say, the point there is that while the network itself was back in 33 minutes, it's the knock-on impact of that on the application. The service is a lot longer because it means
Just
that
fell over,
got to troubleshoot why it's not working, then realize that the server needs a reboot, and so on and so forth. And it's that thing of, if you have the understanding of what the service is and what it constitutes, then it's a lot easier to sort of lay it out and say, right, okay, I know that for this service to work, all of these ducks need to be in a row. I'm going to change this one, but I need to make sure once I've done it, then that all of the other ones are still in a row, so that the service continues to work afterwards. Or you come up with the alternative way of making sure that it stays up through redundant paths or whatever else, right? So,
that was a good 7 or 8 years ago, and the pressure then was like intense on that type of environment being up. So now it's probably like, it must be 100% like uptime. So you have to have like ISSU type stuff. But it's a classic. I'll not dwell too much more on that. But you were hearing things like,
it leads
is there a spanning tree loop on the network? Is that why they have, and things like that? It's like, no,
exactly that. And again, that's why you need to have that mapping, if you like, of a service to the infrastructure it passes across, and why the visibility we talked about before, that why that visibility is such a key part of this, so that you're able to understand the mapping and be able to see which parts of the environment are failing. So really.
It was the guys that worked in the warehouse that were saying to me, "Is there a spanning tree loop?" So they'd obviously heard that. They'd obviously heard that before. I was like, "No, it's not a spanning tree loop. It's is your laptop working?" Yeah. Like, okay, so it's the application. And
so it's not. It's not.
I guess that was our whole part of one of the points of doing this Network Freestyle is to give some like war stories. So that was
totally. I mean, yeah.
Availability perspective, but there you go.
No, I mean, and I guess we've all got those type of things. I don't know, beeping headsets for wireless headsets in a warehouse, which mean that the headset's lost contact with the server back at base, and it could be down to any of the elements of the wireless or the wired that make it happen. Wireless, in that case, for me, wireless LAN controllers, dropping off the network, and so any authentication as the headset joins the network was screwed because et cetera, and those devices are in a data center somewhere, way out of the actual traffic path. But it's that ancillary thing of there's an element here that's involved in the process, and that's why you need to think that bit wider and cover all of these things, I think. So I mean, any other war stories along the way, just shout up. It's all good.
We'll try to keep on track time wise this time, so I'll shut up from that perspective from now on.
No, it's all good. So we've covered some of these ideas. I guess to just drill into them a little bit further, we talk about redundancy, and that's a pretty standard approach to availability from a network perspective, and that we can do that at different levels, right? We can have redundant hardware in the network. We can do redundant circuits or links between the hardware. We can even build completely redundant networks if the level of availability and the cost of losing a network is that great. Then do we build an entirely separate network to support a failure scenario? And that kind of leads, I suppose, to DR, because that's essentially what DR is, right? So all of those things. So redundant hardware, you might be talking about, right? Okay, well, where we've got connections to one switch, we'll connect to two instead. Where we've got one router terminating two circuits, what we'll do is we'll change that over, so we have two routers connecting a circuit each. Those
example of that is if you take a step outside of the enterprise environment that has like a DR data center with some form of like replication, another completely redundant network is the internet exchanges. So for example, London Internet Exchange, I think that's based on like some two different vendors, like I think it's Extreme and Juniper. So they have like exactly the same network. So if they lose one from a software bug or something, then the other one doesn't go down. So
exactly, and it's down to the criticality of the service, right? So obviously in that scenario, what you've got is a service that's consumed by hundreds and thousands of customers. That if you lose that network, your impact is immeasurable, isn't it? In that sort of scenario, certainly these days.
And this year, was it this year or back end of last year, that O2 had a major outage that they said was due to. So O2, for anyone who's watching this from outside the UK, O2 are like they're like Vodafone, Orange type mobile cell carrier in the UK, and they have they're one of the leaders in the UK, and they had a complete network outage for multiple days. I think the root cause at the time anyway, or the week or a couple of weeks after, was it was a software bug that. So yeah.
So it goes to show, doesn't it, that under some circumstances, a redundant network is necessary to support applications. It's a compromise, isn't it? It's something to be borne in mind, that if a cost justification can be found, then that's where the trade-off is. So it's all got to be thought of and considered, isn't it? So when we were talking before about the multiple circuits, multiple links, you could create a justification based on the amount that it would cost to implement that, as opposed to the amount that it would save if there's a failure. That's the conversation that needs to be had. So once you've introduced that redundancy, I suppose you've then got some technical challenges, because you need to be able to work out, well, how do I now use that and put in place some way of ensuring that the redundancy doesn't impact the network as it stands, but B, that when something does go wrong, that it works, it fails over. So both of these two, really, the sort of loop prevention scenario and the convergence, are kind of intertwined. Again, from a network perspective, you've got two different levels to think about this, and yeah, we're getting down to layer 2, layer 3 stuff here. So the dreaded spanning tree is about to make an appearance, and I'm going to bring these two together because they are kind of interrelated. But essentially, yes, you've got layer 2, so where you've got that layer 2 connection, or in the redundancy, you need to be thinking about spanning tree. And And you need to be considering, right, well, how do I use multiple layer 2 connections if I'm going to put them in there? Spanning tree, from a loop prevention point of view, obviously what that's going to do is going to block one of the redundant links. In a failure scenario where an active link fails, then spanning tree will open up that previously blocked link and allow traffic to pass over there. There is a period of convergence time to make that happen, and it varies, and I'm not going to go into the numbers because I'm way past all that sort of stuff. I can't remember them for the life of me. But in essence, there's a number of seconds that will happen depending on what version of spanning tree you're running in order to restore service. So you may look at other ways of using those redundant links, and people who are watching this who've done any sort of CCNA, CCNP, you'll know exactly what I'm talking about. So there's the multi-chassis ether channel, or MEC, or VPC, or switch stacking, or whatever you want to call it. The bundling together of loops of links between multiple switches that allow you to use them as a single link, and then if should one link fail, you basically reduce the size of the path through the network. You're not then running spanning tree because you're not blocking anything, so you're using both those two links, and so it's nicer, but it brings its own challenges in terms of how the switches and the network infrastructure are configured to make it happen, right? Don't say the word VPC to me. I'm not a fan, but the Nexus switch in particular, with its implementation of multi-chassis ether channel, has huge challenges and dark times, my friend, dark times.
Yeah. Very, very high level. Like, so in the Cisco world, there's VSS, which is virtual switching system, and that's basically, well, there's VSS, and if you can, that's analogous to stacking, basically. So you've got two devices or more potentially, depending on the vendor, because some of Cisco's competitors you can do more than two, but equivalent to VSS. And I guess like with the Stackwise Virtual, is it called? I think that's coming out, where you can you can stack multiple devices via fiber ports. If it's not out, it's on the roadmap. I've deployed it on. I think I've paid it 3560 CXs actually.
Yeah, it's certainly out there and in use.
So anyway, that's kind of like it makes like two. Let's just keep it simple. Two switches act like one, right? At layer 2 and layer 3, so you've got one default gateway, one layer 3 default gateway .1. You don't have to run HSRP. You can do a port channel, layer 3 port channel. No, you can't actually. You can do a layer 2 port channel to an SVI, a single SVI, rather than running HSRP. So that's with VSS, but with VPC, it splits out the layer 2 and layer 3 aspect of it. You can do a layer 2 port channel, but you still have to run HSRP. There's a link in between the two switches, which isn't much use to anybody, called the VPC peer link, and it can cause issues with routing, blocking traffic going from left to right, right to left, east, west, all that kind of thing.
Yeah, I mean,
another show, but yeah, I get it. I get it where you're coming from.
In a pure layer 2 sense, it's fine, but it's the complexity of what you're trying to achieve versus the benefits of doing it. I'm just not a fan, but that's like you say, one for another time for sure. Obviously, we've talked about layer 2. We've got layer 3 to consider as well here. So this is the sort of IP routing side of things. So we look at how we configure our routing around redundant links and what that's going to work. And typically, that's using your routing protocols, which, again, a topic for another time. And certainly for those who are doing their certifications, they'll know this stuff inside and out. But yeah, there's things you need to concern yourself with there around convergence times and the way those routing protocols operate, as to how quickly they're going to converge in a failure scenario. And as I say, one for another show probably, but there's all kinds of variables there that you need to concern yourself with, right? So
I would just say what a one-liner on that from my perspective is,
yeah,
BGP can be as fast as anything else.
BGP.
There's a myth that BGP is slow, and it can be. It is out the box potentially, but it can be really fast as well, and give you a lot of flexibility at the same time. But it takes some tuning potentially. But
so the tuning, right? Okay. Well, the other thing that I was just gonna drop on here for reference was 3 magic letters, BFD.
Mm-hmm.
I'm a big fan of BFD for all kinds of reasons, but I think it helps, right? It helps with certainly with some of the routing protocol capability. And if you're using static routing, it's invaluable, because obviously what it's going to do, right, this is bidirectional forwarding detection. Essentially, what it does is you enable it on an interface, and you enable it on a neighboring interface along the same layer 2 path, and in fact, let's just say on the same subnet. And what the interfaces send hellos to each other, and you can basically tune the timers down to the tens of milliseconds if you feel that way inclined. As soon as the device at the other end disappears off the network, if there's something in between that causes that to stop talking or stop being heard, that interface gets taken down. And when that interface gets taken down, the router does its or switch does its thing and is able to fail to its next the next route in its rib much quicker than allowing a routing protocol to converge around failure, a soft failure, if you like. So it's a really useful technique for that. I don't know, Malc, any thoughts on that?
Yeah, the only thing that I'd add, and I'd done BFD to death during the CCDE studies, that's why this springs to my mind. But the biggest advantage of BFD, because what are the alternatives? This is about failure detection, nothing else. So if you've got slow everything else in your convergence or your routing protocol, so let's say that your other timers, to detect the link failure, it could be like 1 millisecond or 30 milliseconds with BFD, or 50 milliseconds, right? So that detects the link, goes down. After that, you've got other things like you've got to tell everybody else. You've got to tell everybody else it's down, as in, like all your neighbours. You've then got to calculate a new path, and then you've got to install the route into the rib, and so does everybody else. And that's when everything's converged. So
Absolutely.
BFD is only one part. The thing that would draw a parallel to it, what are the alternatives? The alternative is, if you have like direct connected links with nothing in between, that's carrier detect, and as soon as the link disappears, it goes down and it tells the routing protocol.
But even there, if you've got a software problem at one end or the other, won't detect that necessarily. But yeah. See, I take your point.
Yeah, and then the other main option for failure detection is timers on routing protocols, and this is the main point that I wanted to highlight. Why would you pick BFD? So you could lower your BGP timers to like 1 and 3 seconds, or you could reduce your OSPF hello timers to 250 milliseconds and 750 or 500 milliseconds or whatever. But then the whole on dead is like constantly being sent by OSPF as a process. Let's say on that same box you had EIGRP running.
Yeah.
What you would do is you would lower the EIGRP hello and dead timers. That's another process that's sending fast hellos, they call them.
Yeah.
Now, BFD differs, as BFD is one process that's sending these fast hellos, but you can subscribe different protocols to it. So
And
it lowers the CPU cycles
I
that's
was going
being
to
used
say
in the
it's a
top.
really lightweight process as well, right? So
Yeah, that's all I would have to add
no,
to
no,
BFD. Yeah.
I mean that's really valuable, because I think there are ways. I mean, and of course, BFD, you're applying that to any routing basically that passes over an interface, right? So it doesn't just work for one routing protocol or another. It works for, well, most within Cisco, and I'm sure similarly across other vendors as well. So moving on, we'll look at we talk about SSO, and we've kind of touched on this already. The idea with SSO and the stateful switchover is that you have multiple devices or appliances. Now, this tends to be used where you need appliances to maintain state about what's passing through them. So rather than from a sort of switch or routing perspective, this will be more lending itself to firewalls, to wireless LAN controllers, these kinds of devices in a network, I think it's fair to say. You can have them two or more, I guess, in an SSO, a pair or cluster. So I'm just going to scribble that, pair or cluster.
It can also retain the state for a routing protocol's entries. Like, so for example, in a dual supervisor chassis or something.
Actually, that's a really valid point. Actually, yeah. So in that sort of scenario,
if the chassis fails, then it's got the state, and then you combine it with non-stop forwarding, so it just uses like a frozen state.
yeah.
So it won't converge, but it'll continue to forward traffic.
So it's a snapshot of the previous state, isn't it? And then once that failover occurs, then up starts the routing process on the failed over device, that will then, once it's in and up and talking, it'll then start be able to update and change the state.
Refresh everything. Yeah. One thing all saying it is SSO and BFD, and so SSO non-stop NSF, which we don't really need to go into that, but non-stop forwarding as it continues to forward the traffic in the chassis. SSO / NSF kind of come together normally if to achieve and it's all around fast convergence and identifying blah blah blah. If you use SSO and NSF with BFD, they'll break each other. Not going into it now. Google it. There's loads of stuff, but they break each other.
Yeah,
so
that's fair. That's a fair point.
Yeah.
Like I say, I mean, the main elements, I suppose, of SSO are that ability to detect when a failure's occurred, and then the switchover itself. Now, again, there are implications depending on the devices that are concerned. We've already mentioned there the stateful switchover between two supervisors in a switch, for example. There'll be implications there in terms of what state is carried across, what state the switched over appliance or supervisor will be in at that point, and what that means for the network traffic that's flowing through it. And all of those things have to be borne in mind. For example, in a firewall failover, you'll carry MAC addresses across between interfaces from the active to the standby, or you won't, depending on the platform. And so, what does that imply for ARP entries in the wider network? You might have an issue where connection state will be carried across between things, but routing protocol state won't be, and it has to restart routing protocol. And again, firewalls notorious for that one, where you'll get a failover, it will maintain a level of state, but potentially need then to reinitiate routing protocol with devices that sit around it. So you need to understand those implications. Really key. Any more on those ones? Are you happy with?
All good for me.
Okay, so I mean, really, those are the sort of network elements. I think we've gone through some of the other bits and pieces here about the mean time between failure, stability, performance, but all of those things come together. And I think all I wanted to do was just maybe just go over quickly one example of what that might look like. Are we okay to do that?
Yeah, I think we've got probably about 10 minutes.
Okay, all right. Well, let's have a look at that. So what we'll do is I'll give an example of. We'll keep it really simple. Okay, we've got a PC down here, and this guy is connected to a VLAN, which in turn is connected to a switch, a core switch, which in turn is connected through a firewall, which will connect to an internet connection. And then the other side of that internet connection is the service they're trying to hit. In our case, let's say, why not, Office 365. So our service in this scenario is about making sure that basically that this guy down here is able to get his Office 365 service. Okay, nice and simple. Now, obviously, we've talked about all of these different ways of putting redundancy into the network and so on, and what the implications of that might be. Now, this is from a logical point of view, this is what we're trying to maintain. Okay, this opportunity here where we've got some routing, we've got firewalling in place, and we've got the connectivity out towards the internet. So how might we improve the resilience of that? Okay, so and the availability of the Office 365 service. Well, first up, I suppose, pretty obvious, right? Second router and a second internet circuit into there, and we can connect those two. Let's not do that just yet. Now, clearly, we need to make sure that we've got some failover between these, and in order to do that, typically we'll run a bit of routing protocol up into the internet service provider, and then we'll run a bit of something between the routers as well, so that we're able to fail over between them. Nice and simple, right? We might then connect up a pair of switches inside here to provide the VLAN that connects them.
Here's just a quick question on that then.
Yeah, go on.
And I know the options that I would consider, but and it's probably more of a comment rather than a question, but those switches, think about whether you want to stack them or separate them, because stacking at the edge, unless you've got two stacks, you know, it's effectively a fate sharing scenario. And if it's a critical internet service like an internet pop, the main internet pop for a large campus or the whole company, it might be. Think about that, because that thing that I was talking about earlier on at the start, that bug that drives you to upgrade your new platform 3 or 4 times in a year that doesn't yet have in-service software upgrade, that's 4 or 5 outages on your internet pop.
Exactly that. I mean, there are other limitations there as well, of course, right? You've got distance limitations and whatever else might come into play. You know, these guys might be in different halls in the same DC, or they might be in different DCs. Mm-hmm. And so you may not have the option to stack them or whatever. But yeah, absolutely, all of that. This is part of the point of walking this scenario through, right? Is that these are the things that we have to consider. Fate sharing is an interesting one, and that's kind of, I suppose, where I'm going with this, walking through this scenario, because So we'll come to that in a minute, actually. But I'm glad you brought it up, because it's that's kind of where I was going with it. So it's all good. So in this scenario here, obviously there's a situation where the routers can talk between themselves because they can connect through the two switches. You might have an issue if one of the switches breaks because the routers can no longer see each other, right? So how do we get around that? And is that a problem? Well, yes, it's a problem, because we end up with a kind of a split brain thing going on, right? Where one router might advertise out that it can see the network, and the other one might still, even though they can't see each other and know which is the primary path, which is the standby, and so on. So we need to make this a bit more resilient here in some shape or form. So we end up perhaps connecting these two together with two connections. We may even consider cross-connecting these guys in some shape or form as well, so that if we lose one of the switches, the two routers can still talk. Or what we may do is, instead of doing that, we may have some process on the routers that if it sees the other one's gone missing, has some kind of understanding of, well, I'm the primary and this one's the secondary, and we have a preference for shutting one down against the other. These are the kinds of things that we need to consider, right?
The other option is you could have a link between the two routers.
Or you could just put a link
So
directly between.
If the link between the switch on the left fails, but everything else is still up, it might come in via switch 1 on, well, I'm calling this left 1, right 2. So it might come in on switch 1, and then it could route or spanning tree over, like if that link on the left between router 1 and switch 1 fails, but everything else is still up, and your preferred path out to Office 365 is router 1, then that's where you could either have like the diagonal cross connect type approach, or a combination of that, and you get it anyway. But
and again, it could be down to be availability of fiber, or the cost of the circuits between the two locations, or it may just be that they're next to each other and they just need a Cat6 cable run between them. And these are the things you need to consider, right? All of the above.
Mm-hmm.
So that's cool. So we've got some connectivity there. We've got our VLAN there between, now on the inside of our resilient routers, which is great. So now we come down to the firewall layer, and the firewall, well, we can take our firewall and we can connect it to both those two switches, right? Or can we? Well, in this situation, you've got a choice, right? If you want to maintain a single VLAN across the two, then from your firewall point of view, you can't have two interfaces onto the same subnet. Okay, so then you want to think about bonding those together into a port channel. Now, if you're going to bond those into a port channel, then we need to be able to bond the two switches in some form. So we come back to the thing that you were talking about stacking the switches, or even running the dreaded VPC if those are network switches, Nexus switches. These are the problems we have to think about, right? But then, of course, what happens if the firewall fails? Okay, so if the firewall fails, we need another firewall, right, just in case, as a backup. And if the firewall is required as a backup, well, we need to connect them together, because they need to be able to share state in order to do the SSO failover. And the outside interfaces need to be connected in the same way. So then we need to cross-connect these guys. Okay, so now we're starting to get really interesting here. We need to be able to do some routing from the firewall to the routers. So again, we can choose to do some static routing, maybe, or maybe not. Maybe we choose to do to run a routing protocol. But essentially, we need to do some sort of routing up here. So there's let's say for argument's sake, we choose to do more routing protocol, and we can choose BGP again. MaxNet, it's just an example in this case. Okay, so we've got our resilience. This is all forming up quite nicely. And now, of course, we need to do the switching that sits inside the firewalls for the back towards the user. So again, it sounds like we're going to have to do 2 switches, and in this case, yeah, let's say we'll do a stack this time. Why not? Why not indeed? So we form those up into a stack. Now we need to connect this guy and this guy back into the stack. And obviously, if one of the switches fails, we need to cross connect them. And if we're going to cross connect them then into the same VLAN, then they need to be port channels again. Okay. And so on and so on. And our user down here isn't going to be connected into the core switch. He's going to be connected into an access switch somewhere, all right, out on a floor. And that is going to be connected back into those 2 core switches. And again, if that's a VSS or a switch stack, you're going to run LACP into that as well. Quite fiddly, this, isn't it?
Yeah.
Again, we're going to need some routing coming from those core switches into the firewalls. And if we've chosen to go down the Nexus path, then we've got the limitations that we know already around the routing in the coming from those core switches up to the firewalls. So we can see there we've put in a load of redundancy and resiliency to try and maintain the availability of the Office 365 service from here to here, which is great. But what happens in a failure scenario? I mean, we'll take a particular example of let's say losing the firewall in the middle here. So this guy is the primary firewall. It's currently active, and for some reason, it just stops passing traffic. Right. Well, if it just stops passing traffic, what do we need to make sure happens around it to make the network continue to work? Well, for one thing, we need to stop routing packets to it. We need to pass those to the secondary. So the secondary needs to go active in order for us to fail that over. So the secondary needs to detect that the primary's failed, needs to pick up the interfaces from the primary, and we need to then start passing routing from our core switches to the secondary switch, secondary firewall, sorry. That secondary firewall also needs to establish routing out up to towards the internet routers, and obviously we having switched across like that doesn't impact the internet facing routers because they're still receiving routing updates from the right place. But you can see there that there's all kinds of knock-ons there. There's the SSO of the firewall. There's routing from the core switching, and there's the layer 2 movement of MAC addresses between interfaces on the switches that sit north and south of that firewall. If I missed anything, I think that's.
I think you're good. I mean, I think like the one thing, I think this is a thing I need to probably get a sanity check from you. But one option for that BGP session and that routing session, you could potentially run a BGP session from those like routers at the front end down to the core switch within the VSS through the firewall and allow BGP through the firewall. Yeah.
So this is exactly the point, right? So there are ways and means you tune this and you change it based on what you're talking about.
Yeah, that would be like, I don't like, the standard blanket policy. I'd prefer not to run BGP on my firewalls because a firewall is not a router. But so you could, but that's a design that I've not really seen implemented a lot. Like the front end BGP into the back end with a firewall in the middle, but it is an option. So it's maybe just a food for thought. You've not seen it before.
It's absolutely a valid thing, right? But I guess again, it depends on where you're potentially what addressing that you're wanting to advertise out into the wild as well, right? So if you imagine, for example, that that the subnet that sits between the firewall and the router here is your public addressing here,
Yeah.
which is fairly typical, right? Your public addressing sits on that subnet, and then you NAT at that interface through to services that sit behind the firewall. I mean, in that case,
The internet router is like normally, yeah. So that's one option, but one other way. The other way is that could be like just a transit network. So if you look at the diagram on the right, so so that's one design. So you NAT on the firewall, and the firewall is effectively the outside of your network. The other way, main way that I've kind of seen it done, there is the BGP through the firewall way, which obviously the south side of the router would need to be private in order to like achieve that sensibly.
Yeah.
But I've not really seen that in a production environment, to be honest. The main thing that I've seen is something along the lines of an alternative to the public addressing in between is private IP addressing in between the front end switches and the
okay.
So let's work out up from the firewall.
So yeah, I got on with you. So in that scenario, what you'd have is a transit route from those routers, which would be private addressing to the outside of the firewalls, and then public addressing inside the firewall, or as
not quite. I'll explain it quickly, right? So see how we were talking about, like, let's say we had like the crisscross lines between the routers and the front end switches as well. So if you draw diagonal lines in.
Let me draw it out here. So so what we
you only need to draw as far as the firewall, right? And then just for the hell of it, draw that one as well. Now, if you put like a routed link between the switches and you draw the firewalls in, just as you've got it in the diagram to the left, pretty much, right? And this is another design, right? So let's say like you're a big company, you have private, you have your own IP space that you advertise from those routers at the top out to the internet. So let's say you've got a /16 for your company, or a / whatever, right? Now that's public north, right? South of those routers, you would run private between the routers and the switches, or you could run private, right? RFC 1918, and then there would be a link across between the two switches as well. So that RFC 1918, you could run like OSPF. And the reason that you would run OSPF is to advertise a default from those. Even let's say you receive the full internet table in the routers at the top.
Yeah.
Like the full BGP table, right? Yeah. But to your enterprise, you would only advertise a default route into OSPF as far as the switch. And then between those switches and the firewalls, you would just have a static default north and a static RFC 1918 south.
Okay.
That's another way to kind of.
Yeah. I'm with you.
But obviously that adds like a whole load of routing, redundancy, tuning, and all that.
Yeah, and this is kind of the point here, right? We've got interaction surfaces here, and this is one of the definitions of complexity, isn't it? Is that where you've got lots of elements that basically have a lot of interaction between them. The bigger the interaction surface basically is the increasing complexity. So yes, I mean this is absolutely a valid way of doing it. Depends, as always, right? I've got another one.
Really doing it if you're receiving the full internet table, because the reason that you're doing that is you're sending a default route and you need to get it to the default route, but then once it gets to either router 1 or router 2 on the left and right, respectively, it then says, well, in order to get to internet destination, it's better going out ISP1 or ISP2, and then it can use that cross connect link which is running OSPF, because sorry, that cross link would be IBGP, for example.
Yes.
Yeah. Anyway, sorry. I don't want to distract you from what you were talking about.
Don't apologise. This is the point, right? That there's a lot of interaction that you need to consider in that scenario. Like say, if you've got the statics pointing to the switches, in that situation, your statics would just be pointing at an HSRP address, right? To the switches.
Yeah, /29 or something like that. Yeah.
Yeah. And the switches have effectively the same routing table because they're cross-connected to the routers. And so are receiving routing updates from both routers. So there's effectively the same routing table. So if you lose one switch, your failovers, so long as the other switch is still there, and you can fail in this scenario where you've got your statics, you might choose to you might choose IPSLA or something like that in order to force over the routing to the alternative. Oh no, you wouldn't need to do that because you're pointing at the HSRP address. So use an HSRP failover now for where you lose one switch, right? So again, it's HSRP failover. It's then the OSPF has learned the routes out to the routers and all's good. If you lose one of the routers, then obviously the switches need to realize that route has gone missing and withdraw its routes from the routing table, and then start using the other alternative path. It's all of the above, right? There are other ways you might choose to use to not depend on using routing at all, and using routing protocol at all, and use statics right up to the routers at the top. I had a scenario where I chose, let me just draw it out again. But if you've got a situation where you've got two routed connections which are with the same ISP but to different locations, doesn't actually matter in this situation, but you can cross connect those through the switching infrastructure or not. And then down on the firewalls, what you would do is you would basically have two sets of statics over what's going to be your primary. You create a 0.0.0.0/1 and a 128.0.0.0.
I like that one. I've never used it, but I've thought about it.
This works a dream as well, let me tell you. And then via the other path, you just have a default, right? And that basically points to your secondary. You use BFD or IPSLA or whatever you choose to use. In this scenario, what we used was IPSLA actually, from this guy to the next hop here. So IPSLA to monitor the availability of this guy, which meant that we could track this circuit being up, this router being up, and the connection there being up right the way down to the firewall. Any of those lost, the /1s get withdrawn, and it fails over to the default route, which points to the secondary. Which again, you just track. You have a track route on the default route. So it depends. I suppose that's the point of drawing all of these out, is that you want to keep it simple. So logically, the left-hand side here, all of those solutions that we've just drawn out there actually are the same logically. Yeah, they've all got the same VLANs, the same subnets, and the same routes there effectively, same path. But each one has different characteristics based on what type of failovers we're looking at, whether we're looking at SSO, whether we're looking at routing protocol, whether we're looking at spanning tree, whether we're looking at multi-chassis ether channel. And it's that fate sharing that kind of decides which path you want to go down with this. You know, where the physical locations are, what the infrastructure looks like in those places, and more. It's that pragmatic approach again, right? It's understanding, where are the trade-offs in taking each of these. What are the interactions like? How complex are the solutions, and how supportable are they in order to make this as available and redundant as possible? I think that's all I wanted to sort of talk through. It's kind of, it was always, when I wrote the blogs and when I've done the stuff before, it's always been about discussion points. I think you can kind of see what I'm getting at with this. I'm not being prescriptive. I'm not saying here's the solution, this is what the thing is. Do you see what I'm getting at? I think we're sort of coming from the same.
Definitely. I mean, like even with these designs, you put it in a different environment, and it can look, it could be tuned like differently. Like so, but these are conceptual designs that you're talking about, or we're talking about here.
Yeah.
And just because we said like this is a way to do it, there's different variations even on those those are, if you think about these that are on the screen, they're models.
Totally.
Like you might need to, for example, probe something even further up in the infrastructure. In the last one that you drew, you might you might not have equipment to run OSPF or EIGRP, or you might be forced into something at that last part of the RFC 1918. You might have a tactical solution in for 6 months in the middle diagram where you've only got like one switch and one internet link, while the second internet link is being delivered by the carrier, but you have to plan for that anyway and then integrate it as seamlessly as possible. So
exactly.
It's not just about the design, it's thinking about in the future, how can I design this so that it can be available in the future, but also whilst I'm getting to where I want to get to, how can I put it in the most optimal way for this environment?
And that's exactly, I mean, we mentioned talking about the redundancy and everything there, and that's a valid point. Actually, it's probably another thing to add on here is the fact that there's migration activity and whatever involved in this as well, right? Because things are always changing, and you're always having to consider, right? There's an old network and a new network, and how do I get from one to the other, and how do I maintain availability over that period of time? And all of what you just said, But I think the whole point is that you can see availability. I guess when it comes down to it, availability is much more than just, right, how do I put some redundancy and resilience into this? Look at the big.
Next time someone says to you, see that new network that we're getting, it needs to be available.
Yeah.
Tell them to watch this.
Please think about the big stuff for sure. Awesome.
Cool. We're done.
I think we're good, right?
Yeah, all good.
Excellent. All right. Well, listen. Any comments, corrections, criticisms, as usual, always welcome. Guys, you can contact us at @netfreestyle on Twitter. You can email us at networkfreestylers@gmail.com, which we had some good feedback over recent weeks on the email, and I think on LinkedIn as well, right, Malcolm? It's been really good to see. Or leave comments on the YouTube channel, and again, the comments on the blog as well at networkfreestyle.tech. Really, as always, really interested to see what you've got to say. And thank you very much for watching. And thanks, Malcolm, for some awkward questions.
Happy days. All good. I'm sure you'll return the favour. Thanks, everyone, for watching, and see you in the next one.
Yeah, enjoy.